This is chapter 7a. We're going to cover the central limit theorem for sample means. We're going to start off with the law of large numbers. This is different than the central limit theorem. This says that if we have large sample sizes, then the statistics that we get from those samples become more accurate. The idea here is that when I take a sample, if I have a sample of size 20, whatever statistic that comes from that is going to be better if I were to instead have taken a sample of size 40. And it would have been better if instead I had taken a sample of size 60. It just says as my sample size gets bigger and bigger, the statistics that I get become more accurate. And here what I want to make sure we're thinking about is the fact that when we deal with a mean, we have a sample mean, and we've been saying this whole time we're going to use that to make an inference on the population mean. As one example, we could do it for any metric. We'll just take means for now. And that's this idea that X bar gets closer and closer and closer to mu as my sample size gets bigger. We also have the idea about a sampling distribution. This is a very weird concept for a lot of people at first. We've been using the phrase distribution throughout this course, and when we've talked about distributions, if there's no adjective in front of it, when we say distribution, we mean distribution of data. So you can think of that as an implied word previously when we said what's the distribution of something. It's just of data, right? When we say something has a binomial distribution, we say something has a normal distribution, or when we say what's the distribution of X, or what's the distribution of any variable, we're talking about data. We're talking about individual observations, okay? And I want to make sure that we've got that down before I start into sampling distribution here. We're talking about when we say just distribution by itself, we're talking about what do individual data points look like. Think about a binomial distribution, right? A binomial distribution is a bunch of individual observations of succeed and fail. The accumulation of that makes up a binomial distribution. When we say, people's heights follow a normal distribution, that's individual people having a height, and when you put that together, we have a normal distribution. Okay, so when we say just distribution, we mean of individual observations of data. When we have the adjective in front of it, sampling, when we say sampling distribution, we mean something different. We still mean distribution in the same way that we did before, in that we're thinking about what is its shape, center, and spread. But now we're not talking about distributions of individual observations, individual people, individual trees, individual computers, individual cities. Now we're talking about the culmination of statistics. So it's this idea that instead of saying, people's IQs follow a normal distribution. Well, what does that mean? That means if I were to go take a person and get their individual data point, I could have an IQ, and then I can go to the next person, get their IQ. That's another individual data point. I could put all those individual people's IQs together, and the shape would be this nice little bell curve with a certain mean and a certain standard deviation. Now, I'm not getting individual people, I'm getting statistics. So we're kind of inceptioning this. We're kind of going another layer deep. Now I'm not getting individual X values or individual Y values, whatever variable you want to call it, for individual people. Each observation in this case is not an individual person, but it's a statistic. Okay, so this is a weird concept, but now I'm going to go out and I'm going to get an X bar, not an X. So the idea is not I go out and I get one person's IQ and that's one data point. It's I go out and get a sample mean of IQs. That's a data point. That's an X bar. That's a statistic. That's one of them. Now I got to go do it again. Now I got to go do it again. Now I got to go do it again. Just like I would build up distributions by getting a bunch of different people's IQs. If we're talking about a sampling distribution, I have to go get a bunch of different sample statistics. This definition is written in small font rather than big font. So this is not one that you have to write down in your notes. The reason for that is the definition isn't really overly helpful. So I don't want you to think that you need to memorize the definition of this. You do need to know the definition of law of large numbers because that's helpful. Because if you know the definition, you can apply it. It's very straightforward. Law of large numbers right here. If we have a big sample size, then sample statistics become accurate representation of the parameters. The statistic gets closer and closer to the parameter. It becomes a better guess. I mean, it's pretty intuitive. It's pretty straightforward. I have you write that down because you need to know the law of large numbers. You don't need to know the definition of a sampling distribution. It's kind of a weird concept, but you need to be comfortable with it. So I'm not going to ask you to define a sampling distribution, but we are going to use them a lot. So if you need to rewatch this a few times, do so, but make sure you are comfortable with this idea that up until now we've been talking about distributions of individual data points, but now we're talking about distributions of statistics. Before it was going out and getting a bunch of data from individual people, and now the data is actually statistics. And when we see statistic, if you want in your brain, go ahead and substitute your favorite statistic in there. We're going to talk today about X bar as a statistic that's a sample mean. So we're just going to go ahead and sub that in if that makes it easier for you. Instead of getting a bunch of individual people's IQs, we're going to get a bunch of mean IQs. We're going to go take a sample of 20 people and get their IQ. We're going to get another sample of 20 people and get their IQ. Take another sample of 20 people and get their mean IQ. All those X bars, when I put those together, that's a sampling distribution. And the properties of interest for a sampling distribution are the same properties of interest when we just have any distribution. Shape, center, and spread. So there's no difference there in what we're interested in when we talk about a sampling distribution versus a distribution. It's just a distribution on something different, but the properties of interest are the same. When we talked about shape before, we generally talked about skewness. We're going to kind of shift a little bit away from skewness and talk about what the actual distribution is. So of course, when we say something has a normal distribution, we mean that that is a symmetric distribution. When we talk about center, we typically talk about mean, we talk about spread, we talk about standard deviation. Now there are other methods of those, as we talked about back in chapter 2. It's just ones that we don't tend to cover at this level of a statistics course. And so this is where the course gets a little bit interesting, because now we start talking about, we shift from talking about what do we know about X to what can we know about X bar. And so you might ask, what's the purpose of this? Why do I care about the difference between any distribution and a sampling distribution when I'm just interested in shape, center, and spread for both of them? And that'd be a good question. And the question is, the answer to that question to me is, what are we trying to do? In chapter 6, we were attempting to answer the following question. What is the probability that we randomly select one person, and that one person happens to be in whatever variable that we're talking about, greater than this, or less than this, or in between this and this? That was the base question you were asking. But what if I don't care about an individual person? What if I'm dealing with a collection of people? What if I need to know the probability that the collective weight of people does not exceed a certain amount? Why might that be useful? Well, lots of reasons. Elevators have weight restrictions. Roller coasters have weight restrictions. And I'm not necessarily interested about one person. I might be interested in the group of people. And there are different properties around groups and individual people, which makes sense. I think you can kind of, if you want to pause and think this through, I think you can. You can logic through that, because there's a certain amount of variability that one person has, and there's a certain amount of variability that a group of people have. What do I mean by that? Think about your GPA. Now think about someone's GPA who's very different from yours, whether it's a lot higher or a lot lower, no judgment. And think about the difference between those two numbers. But let's think about, instead, a group of people's GPA. What if I were to take a group of people's GPA and then take another group of people's GPAs? Are those groups going to have the same spread between the two of them? And I think if you think about it, you'd say probably not, because a group of people, especially a large group of people, some of the high GPAs are going to balance with the low GPAs and kind of bring us more towards the middle. And so the average GPA of the one group probably isn't going to be drastically different than the average GPA of the other group. But your individual GPA might be a lot different than the individual GPA of someone you pass on campus walking by, walking to get lunch. And so I care about the differences in these two things because they help me answer two different questions. Again, one question being, what is the probability that we pick an individual person who meets these certain requirements versus what is the probability that a group of people meet certain requirements? And so we've already kind of talked about this a little bit, but we're going to move back to it here in that if we are interested in the mean of X bar, because we need to know the mean of my sampling distribution, we know no matter what the shape of X is, that the mean of X bar is equal to the mean of X. And this is where you're like, whoa, what is happening right now? We're subscripting our mu's because now we need to differentiate between what type of mu we have. And you say, no, wait a minute, how can I have a mu of an X bar that's a mean of a mean? That's precisely the point, right? We said that a sampling distribution is a collection of statistics. So I have a bunch of X bars, but I need to know the mean of the X bars. Why did I choose to use mu of X bar instead of X bar of X bar, right? Well, because when we talk about distributions, we're talking about theoretically all of them. What does it all look like? So we're saying that the mean of all X bars is the same as the mean of the X's. You say, what are you talking about? Okay, how about this? Let's go back to the GPA example. If we were to take the average GPA of all students at this university, that would be mu sub X, right? Because I'm taking the mean of all individual students, right? We're in X, we're in a distribution of X, it's just individual people. So let's say the mean GPA of all students at this university, I don't know what it is, I'm just going to say 3.2. The mean GPA of all students at this university is a 3.2. What that tells us is that if I were to take a group of 50 students and I were to find their GPA, their average GPA, that's an X bar. And if I were to go to another group of 50 students and find their average GPA, that's another X bar. Then if I were to go to another group of 50 students and find their average GPA, it's another X bar. And if I were to take all those X bars, if I were to keep doing that over and over and over again, then the mean of all of those X bars would just be that same 3.2. What it means is if I were to take the average of all the X's or I were to take the average of all the X bars, you're at the same number, okay? And I want to go back real quick here just to something that we skipped over and make sure we catch. Notice though, I said about the same size, okay? These statistics have to be computed from samples of the same size drawn from the same population. Okay, so I can't take a group of 5 students and get an X bar and a group of 50 students. They have to be the same size. And now you sit here and you say, wait, why would anyone ever do that? They wouldn't. They wouldn't. And this is precisely where this course starts to get weird, is because why are we talking about something we would never do? Here's why. When you don't feel well, you may say, I need to take my temperature. Okay. You take your temperature and you get a reading. That's one X value. How do you know if the X value that you get is good or bad? How do you know if it's okay, or how do you know if it's a fever? The answer is you know what all of the X's look like. You know what everyone else's temperature is, or you can think about it a different way. You know what your temperature normally is. You know what theoretically all temperatures look like. You don't take your temperature every minute of every day and build a collection of X's. You don't do that, but you know what it looks like. And if you don't know what yours looks like, you know what everyone else's look like, and you kind of assume you're probably in the same boat. Maybe you don't know exactly if you run a little bit hot or a little bit cold, but you know what generally people's temperature is because you have this idea of a theoretical, what do the world's humans' temperatures look like? You don't think about it that way, right? That's not a thought that's probably ever entered your brain, but that's the reason why you know that if you have a fever, it should be if a temperature of triple digits, you say that's probably some sort of a low grade fever. If it gets above 101, 102, whatever it may be, you say that's actually like that's a concerning fever, right? 105, you're like, I go to the ER at that point, right? I don't just take medicine, right? Because you know what temperature should look like. And so yes, we're in a really weird world where we're never going to actually find mu sub x bar. We're never going to actually go get 50 students GPAs and find an average, and then go get 50 students GPAs and find an average, and go get 50 students GPAs and find an average. We're never going to keep doing that and then build up our own little distribution. We're not doing it, but we need to know what the theory looks like so that we know what to do with our one x bar. And so they got a little wordy, but I want to make sure you understand that we are deep into the theoretical world here, and we do that for the purposes of us saying, I'm going to have an X. I'm going to have my own temperature. Or I'm going to have my own X bar, the average weight of people. And I'm only going to have one, but I need to know what all of them would look like so I know what to make of mine. Okay? And so that's why we're in this world. So we've addressed one of the three properties that we're interested in, Shapley distribution. We need to know its shape, we need to know its center, we need to know its spread. We've talked about center. We're going to come back to shape later. For spread, the standard deviation of the x bars is equal to whatever the standard deviation of the x's is, divided by square root of n. And this is what I mentioned we'd kind of already covered a little bit. It was subtle in there. But when I talked about that GPA example, when we said the difference between your GPA and someone else's GPA might be relatively large, spread is, is measured by standard deviation oftentimes. So the disparity between two people, that spread, that could be calculated by a standard deviation. The spread between two people might be relatively large, but when we start talking about groups of people, the spread starts to shrink, right? The average of 50 students, one group of 50 students might be 3.18, and the average of another group of 50 students might be 3.15, and the average of another group of 50 students, et cetera, et cetera. They're going to be relatively close to each other. Oh, that's an idea of spread. How spread apart are all the data values? It's this idea that as my sample size gets bigger, my spread gets smaller. This might be an opportunity for you to pause the video and think through this from a mathematical standpoint. When we divide by a bigger number, the overall number gets smaller. So as my denominator, my sample size gets bigger, the spread of the x bars gets smaller. And then for shape, we can say that if we have a normally distributed population, the sampling distribution of means will follow a normal distribution. Now remember, sampling distribution just means what are all the possible values of the statistic? What do they look like? What's their shape, center, and spread? This is the sampling distribution of means. We could talk about the sampling distribution of any other statistic, of medians, of modes, of sample proportions, of standard deviations, right? And we will get to some of that later. A lot of it we won't. It's more advanced statistics to get into those ideas. Right now, we're just talking about the sampling distribution of means. So think about that as the specific statistic that we're talking about. But we know that if the initial population, if X is normally distributed, then X bar is also normally distributed. And that's what I've put here in symbols. If X is distributed normally, then X bar is also distributed normally. And I'm adding in, I know its mean and I know its standard deviation. Remember, we talked about this before. If you identify something as binomial, you can always identify N and P. If you identify something as normal, you can always identify mu and sigma. Now, in this case, we have to get a little bit more complex. It's why we're using these subscripts, because we're saying this is mu sub x bar. Well, what is mu sub x bar? It's whatever the mu of x is. And we will get out of the symbols quickly, because when we see a problem, you'll get to put a number there. But for now, we're using the symbols until we get to numbers. Right? We don't have numbers yet. We don't have problems yet. We're still talking about the concepts. And the same thing, the second piece in that parenthetical is the standard deviation of x bar. So it's just go find whatever in the problem, whatever the standard deviation of x is, divide that by square root of n, whatever that number is, boom, there's the standard deviation of x bar. Now this holds true if my initial population is normally distributed. So if I start off the problem and we say heights or IQs or whatever it may be follows a normal distribution, then boom, I can say that the sample means of heights or IQ or whatever also follows a normal distribution. And now I'm set. I know the shape. We already covered the center, and we already covered the spread. Now the question follows, what if my initial population is not normally distributed? And that's where the central limit theorem comes in. So this is your checkpoint one. Anytime we have a problem and it says find the probability that, and it's a sample mean problem, Then I have to say, okay, it's a probability of a sample mean. I need to know the shape center spread of the sample mean. I'm going to say, is my initial population normally distributed? That's your checklist. If you see a question that's probability of a sample mean, you got to say, okay, I need to know shape center and spread. I'm going to start off by saying, is the initial population X normally distributed? If it is, boom, here we go.